Good day. Let me introduce you to my class. Lexi, turn around. Thank you very much. I want you to observe how my classroom is organized. Think about it. Just look and think about how my classroom is organized. Look at the shapes of all of the students in the class. Look at all the students together. What does Roy, Kim, and Jill have in common? What do Bob, Pam, and Anna have in common? What do Bill, John, and Lexi have in common? Let's change our perspective a little. What does Roy, Bob, and Bill have in common? Kim, Pam, and John. What about Jill, Anna, and Lexi? Well, I was hoping you would say that my classroom is organized by rows going from left to right and columns going from top down to the end. And this is what matrices are. Matrices are an arrangement of values in table format, and these are organized by rows and column. So let's get into it. So Roy, Kim, and Jill, they are in row 1. That's our first column, or first row. Bob, Pam, and Anna, they are in the second row. We'll call row 2. And Bill, John, and Lexi are in row 3. There you go. Row 3. Roy, Bob, and Bill are in column 1. That's what I call C1. Kim, Pam, and John are in column 2. That's what I call C2. And Jill, Anna, and Lexi are in the final row of this one, which is final column of this one, which is C3. So notice that the matrix is organized by rows and column, and we'll always start off with rows first. For this particular matrix, how many rows does it have? And look at the number of columns that it has. So when we're talking about the order or the dimension or the rank of a matrix, we look at the number of rows by the number of columns, and we don't multiply them, we don't multiply them. So the number of rows that we have is 3, and the number of columns that we have is 3. So this is what we call a 3 by 3 matrix. The 3 by 3 will represent the order, the rank, or the dimension of the matrix. Some people say size. All of them mean the same thing. Just telling you the amount of rows you have in the matrix and the number of columns you have in the matrix. As for my classroom in this example, we'll have 3 rows, 3 columns. So it's a 3 by 3 matrix. Let's play around with it. Let's say that I'm going to take off the last row. So now my matrix has 2 rows and 3 columns. So in this case, the order of my matrix will no longer be a 3 by 3, but 2 rows by 3 columns. So it will be a 2 by 3 matrix. Let's say that I'm going to remove this column. What will be the order, the dimension, the rank, or the size of this matrix? Number of rows by number of columns. So it's no longer 2 by 3, but it's 2 rows by 3 columns by 2 columns. So it's a 2 by 2 matrix. What if I took off the last row and the last column? If I took them off, Would that still be a matrix? Well, yes, because it has one row and one column. So this is no longer 2 by 2, but a 1 by 1. And this matrices or matrix is what you call a scalar matrix. One row and one column, which is just a single person in this case, who is just Roy. The things inside the matrix are what we call elements. So Roy is an element of this matrix. Kim is an element of this matrix because they're inside the matrix. So these are what we call elements. And we refer to elements by their position in the matrix. And when I speak of position, I'm talking about the row number by the column number. For example, Roy is in which row? He's in row 1. Roy is in which column? He's in column 1. So row 1, column 1 meets right here where Roy is. That's the position that we're speaking about. If I spoke about row 1, column 2, who do you think I'm talking about? Search it. Row 1. Inside row 1 is Roy, Kim, and Jill. But we don't want column 1, we want column 2. So row 1, column 2, we're speaking about Kim. Let me switch it up on you now. So if we're talking about row 3, column 1, who am I speaking of? Row 3, column 1, we're talking about Bill. Let's play some more. If I wanted row 2 and column 3, who would I be speaking of? Row 2, column 3, we're talking about Anna. Let me see if you can guess this one now. Which position is Jill in? Remember, you have to check the row number and then the column number. Where is Jill? Jill is right here, but here is not specific enough. So when you look at the row that Jill is in row 1 and column 3. So Jill is the element in row 1, column 3 position. So this is how we refer to the elements inside a matrix. We look at the row number by the column number. Here we have matrix A and matrix B. And the elements in matrix A are 1, 5, 2, and A. And the elements in matrix B are X, C, Y, and 7. And we were given the instruction that A, matrix A, is equal to matrix B. Think about it. If you hear the word equal, what does equal mean? It means the same. So it's saying that A is the same as B. In this case, matrix A is the same as matrix B. And the question could be, what is the value of X, C, A, and Y? Now, if A is equal to B, then that means the elements in the same position as A should be the same elements in the same position in the B matrix. So let's look at this one. 1 in A, this is row 1, column 1, should be the same as the element in row 1, column 1 in matrix B. So when I look at it, X and 1 are in the same positions. So that means the value for X is 1. Let's look at this one. Row 1, column 2 is 5 in matrix A. So row 1, column 2 should be 5 in matrix B. That means the value for C is 5. Row 2, column 1 in A, matrix A is 2. Therefore, row 2, column 1 element should be 2 as well in B. So the value for Y should be 2 because these matrices are equal matrices. So we need to find the value of A now. A in matrix A is in row 2, column 2. So I need to look for row 2, column 2, which is 7 in matrix B. So the value of A is 7. So equal matrices have the same elements in the same exact positions. Let's look at this matrix called X. And the order for this matrix, or the rank of the matrix, is the number of rows by the number of columns. Number of rows by number. Let's look at this matrix called X. And the order for this matrix, or the rank of the matrix, is the number of rows by the number of columns. Number of rows by number of columns. It has 1, 2 rows and 1, 2 columns. So it's a 2 by 2 matrix. Notice, once the number of rows is equal to the number of columns, then we call this matrix a square matrix. Just like a regular square that has the same measurements for all 4 sides. Notice there's 2 elements here, 2 elements here, 2 elements here, 2 elements here. So once the number of rows is the same as the number of columns, then that is what we call a square matrix. And if it's not a square matrix and it looks like a quadrilateral, then it's supposed to be a rectangular matrix. For example, if you had a row by column or an order, number of row by number of column, if it was 3 by 2, then this is not a square matrix. Not a square matrix, because the number of rows is not equal to the number of columns. But if you had a number of rows by the number of columns being a 3 by 3, then this is a square matrix because the number of rows is equal to the number of columns. And you can simply write it like this: number of rows is equal to number of columns. This is what we call a square matrix. And square matrices are very important because they are the only matrices that have a determinant. They're the only matrices that have determinants. And the determinants are going to be very useful in helping us to find the inverse of a matrix, which we'll discuss in a later video. Now, this is another type of matrix that is also a square matrix, but it's very interesting because look at the elements. The elements are only ones and zeros. But this element is special and we call it the identity matrix. It has ones along its leading diagonal. Here it is. Along the leading diagonal, it has ones. And on the off diagonals, it has zeros. This type of matrix is going to be very important when we're looking at multiplying matrices and finding the inverse of matrices. So this is what you call the identity matrix. Ones and zeros, and the ones are on the leading diagonal. Let's look at these matrices. So matrix A, bam bam. We want to find out the order, the rank, the dimension, or the size of it, which is really the number of rows by the number of columns. And we want to do the same for B. Number of rows by the number of columns. So when we look at A, it has 1, 2 rows. And when we look at A for the columns, it has 1, 2, 3 columns. So A has an order or a dimension, a size or a rank of 2 by 3. It's a 2 by 3 matrix. And for B, the amount of rows, 1, 2, 3. Number of columns, 1, 2, 3. So this one, B, is also a square matrix because the number of rows is equal to the number of columns. Now, there's something interesting about this one. There's a relationship that I want you to look for, especially here and here. What do you notice? When the number of columns in the first matrix, because the order is important, is equal to the number of rows in the second matrix, then there's a particular word that we use to describe these matrices. Let me write it. Conformable or conformable. So these matrices are conformable. Boy, I need to go back to learn English because the conformable word in our work. Conformable. So we say that matrices are conformable because it is when the number of columns are equal to the number of rows where we can do certain operations on them. Especially when it comes down to multiplying matrices, the number of columns must be equal to the number in the first matrix, must be equal to the number of rows in the second matrix. So conformable means the number of columns in the first matrix is equal to the number of rows in the second matrix. This is what conformable means, and it becomes very applicable when we're multiplying matrices. Let's look at this example. So we're going to test to see whether the matrix C and the matrix D are conformable. So to check conformable, we'll have to write down the order or the rank or the dimension or the size of each matrix that we're looking at. So the number of rows in matrix C is 2, and the number of columns in matrix C is also 2. So C is a 2 by 2 matrix. Let's look at D. The number of rows in D is 3, 1, 2, 3, and the number of columns in D is 1, 2, 3. So this is a 3 by 3 matrix. To test whether it is conformable, we have to look at the number of columns in the first matrix and the number of rows in the second matrix and see if they're equal. Is 2 equal to 3? Obviously not. So these are not conformable. They're not conformable. So they're not fit to do operations such as addition, subtraction, multiplication, etc. So we can't really do nothing with these matrices other than look at them or use them to represent the information. That's about it. So that is why conformable, or I could call it conformability, is important. It allows us to perform several operations, especially large scale operations, such as addition, subtraction, multiplication, dot. So if it is not conformable, then we cannot add them, we can't subtract them, and we cannot multiply them.